when an electromagnetic wave impinges on an atom or a material containing atomic species, but that implies that it could be an ion or a metallically bonded material, the electron cloud is set into oscillation. This situation is like a dipole oscillator and therefore, this dipole oscillator radiates emission all around it in the having the same frequency, and this is we can for a first approximation assume is not direction dependent. This process of this is the basically the process which we call scattering. In other words, it is the electron cloud around an atom which is responsible in combination with the ion cores. We initially consider that the ion core is fixed and the electrons are the ones which are oscillating, and this dipole oscillator sends out radiation in all directions, and this is the process of scattering. In other words, scattering is not merely some kind of reflection, it is actually a dipole oscillator at work. And similar to absorption, scattering is also frequency dependent. So, in other words, the strength of scattering depends on the frequency. Now, there are two possible ways in which transmission can take place. We had earlier pointed out there are three possibilities when light falls on a medium or a ray passes through a medium. One is reflection, other is refraction, and third is absorption. And when you are talking about refraction, we are essentially assuming that the ray is going into the second medium, which we otherwise we call transmission. Of course, if as we shall see soon, if the refractive index is close to 1, in that case the refraction angle, that means the deviation in angle, is very small. The two possibilities are for transmission. Number one, if the medium is extremely sparse, like you are talking about interstellar space, wherein the atomic density or the matter density is extremely small, then the wave may actually pass between the particles. So, schematically I can draw it like this. So, I have my medium which is extremely sparse and my wave is actually passing between the particles. So, essentially there is no interaction, and this is what you can call the trivial case of transmission. But the more common mechanism of transmission, and this is we are talking through a denser media, is the phenomena of forward scattering. In other words, what we normally call transmission, like suppose light is coming from the left of this room and going towards the right of this room, we call it transmission. It looks to us as if it is just motion of light through the medium without any interaction at all, but in reality it is dominated by forward scattering. And when you are talking about molecules in the atmosphere, for instance, the blue color is coming because of the frequency dependence of scattering. In other words, this frequency goes as omega power 4, and that means that the higher the frequency, more will be the scattering and that is why the blue light is scattered, and therefore, we see our sky as blue, and this phenomena is known as Rayleigh scattering. The unscattered light, which is the longer wavelength red radiation which goes through straight, is what is responsible for the reddishness of the sky in the evening, because in the evening what happens, the scattered light is lost, the unimpeded or the unscattered light, the forward scattered light which goes through is the one which meets our eye, and therefore, the evening sky looks red while the daytime sky actually looks blue. So, this is the phenomenon of Rayleigh scattering and therefore, we have to note that what we call transmission in common usage may turn out to be what you might call forward scattering. So, this has to be remembered. That means, the forward wave is reinforced, and if there is no lateral scattering at all, that means all the other waves are destructively interfering, and therefore, we essentially have a wave transmission in the forward direction. But as we saw in the case of the scattering through the atmosphere, often there is a lateral scattering, though the amount may be small, but this is what is responsible for the color of the sky. When a wave is being transmitted from one medium to another, say vacuum to glass, for instance, to take an example, the frequency remains constant. So, what is constant when a wave actually propagates from a rarer medium to a denser medium? For instance, we take the example of vacuum to glass. It is the frequency which remains constant, but the velocity of the wave is altered. In fact, the velocity of the wave is decreased, and the ratio of the velocities of the wave in vacuum, which is a fundamental constant c, divided by the velocity in the medium. So, the denominator is the velocity in the medium, this velocity, this is what we call in common language the refractive index. Therefore, when the wave enters the medium, its velocity decreases, and this ratio we call the refractive index. Though we will not be talking too much about refractive index per se of nano structures material, then suppose I take a glass sphere and keep on reducing its size to the nanoscale, what happens to its refractive index? So, I will mention it in the passing that often as we note here that the refractive index is a function of can be written in terms of the permittivity and permeability of the medium with respect to the permittivity and permeability of free space. In other words, they depend on what we may call the relative permittivity and the relative permeability of the medium, and because these constants or these characteristics of the medium, the permeability and permittivity are not sensitive functions of the size. Therefore, often you will find that even when you approach the nanoscale, the refractive index does not change much, but however, there is expected to be some change. So, we have this concept called a refractive index, which is basically the ratio of the velocity of light in vacuum vis-a-vis the velocity in a given medium. Now, in the previous relation, the Km, the relative permeability or the relative magnetic permeability is actually close to unity, and therefore, Ke is what is going to determine the refractive index essentially. And this Ke is a function of the frequency of the electromagnetic wave, and this is what is responsible for the phenomena of dispersion. Dispersion essentially implies we are referring to some kind of a Newton's experiment, where we send in white light into a prism and we see that it actually spreads into the what you might call the Vibgyor colors, and this is coming from dispersion, the phenomena of dispersion, which essentially tells you that now my refractive index n is a function of the frequency of the material or frequency of the electromagnetic wave, and this dependence of n is coming from Ke, because Km is essentially close to unity. Therefore, because Ke depends on the frequency, we see that the refractive index of a material actually depends on the frequency. Physically, if you look where is this dependence of n coming from, physically you note that the dependence of frequency dependence of n is coming from actually 4 factors. If you include 3 of them are the main factors usually cited, but there are 4 factors here. So, let me write down this as 4 totally, and these 4 factors are what you might call orientation polarization, electronic polarization, ionic polarization, and space charge polarization. And from these terms, it is obvious that I am referring to, for instance, a medium like a dielectric medium, wherein polarization is possible and therefore, I am talking about the propagation of an electromagnetic wave like light, and let me for now assume that light is passing through some medium like quartz or some other crystalline medium, and all these polarizations are responsible for what you might call the frequency dependence of n. That means that these polarizations are activated at selective frequency regimes, and therefore, I mean in other words, these are not active at all frequency regimes, and therefore, there is a dependence of n on the dependence of n on the frequency of the electromagnetic wave. In electronic polarization, essentially you see that because of the presence of an electric field, of course, in the case of a wave, this electric field and the magnetic field are oscillating quantities, because you know that an electromagnetic wave is nothing but a coupled electric and magnetic oscillations propagating through space. Now, because this for now we will assume showing it as if it is a fixed E, but we have to remember that is actually we are talking about and time dependent E and correspondingly a time dependent H. Due to this electric field, what happens is that the center of mass of the electron cloud is shifted with respect to the center of mass of the nucleus, and essentially it is the electron cloud which shifts, and this implies that there is a net dipole created in the material. So, this dipole which is instantaneously created at the atomic level is what is responsible for this what you might call electronic polarization. So, this is actually point number 2, which is electronic polarization. The other possibility is what you might call ionic polarization, and this can obviously happen only in a dielectric medium having ions. In that case, what happens is the center of mass of the negative charges shifts with respect to the center of mass of the positive charges, which means again a dipole is created, and of course, this dipole will oscillate if the electric field E oscillates, and therefore, again there is a dipole being created at the atomic level, and this dipole is responsible for the frequency dependence wherever. And it is clear that suppose I am trying to shift the electron cloud is much less massive compared to an ion. That means that the electron cloud shifting is going to can be operative at higher frequencies as compared to the ionic polarization, which may be active at lower frequencies. The third example is, of course, the third point is orientation polarization, and we have already talked about this orientation polarization when we talked about the case of microwave heating of water. When you put an and we now for schematically show the water molecule, for instance, by this, wherein essentially the oxygen molecule is slightly negative, the hydrogens are slightly positive, and you have these molecules oriented randomly in a medium like water. Now, what happens is that when you apply an electric field, there is a tendency for the dipoles to align themselves such that of course, the positive charge. So, therefore, there is a dipole alignment along this direction, all the individual atomic dipoles or molecular dipoles align themselves and this is responsible for what you might call orientation polarization. Here obviously, when you are talking about entire molecules have to rotate, and this implies that this is going to kick in at even lower frequencies as compared to a phenomena like electronic polarization or ionic polarization. And this, and we also pointed out while heating of water that when the electric field is actually oscillating, that implies that these molecules are constantly trying to rotate and align themselves parallel to the field, and this when dissipatively operates, you can see that actually leads to heating of water in your microwave oven. The fourth of these is the space charge polarization, wherein at any positive Kelvin temperature, you may have actually dissociation of the positive and negative charges in a medium, and this could typically occur at an interface, for instance. And when you apply an electric field, these mobile charges are spatially separated. Of course, these may not be mobile to a long distance, maybe be short distance mobile, and therefore, again you get a net dipole moment in the material, and this dipole moment, for instance, as I pointed out, could be localized to an interface. In other words, there are underlying atomic mechanisms which are responsible for this frequency dependence of n, and these are the four we have just now cited. Now, a few more words about the refractive index. Usually the refractive index is greater than 1, and that means that velocity of light in a medium is going to be greater than, is going to be smaller than, and this is velocity of light. Of course, this is true for any electromagnetic radiation, but I am just writing it for light, is going to be less than c, which is what we expect, because we know c is the upper limit for velocities in nature. Now, there are materials in which n is less than 1, and still we are talking about a positive kind of an n. And this is very surprising, because if n is less than 1, it implies that light is travelling faster than the speed of light, which is an apparent contradiction to the theory of relativity. And the word apparent is used because in reality it is not in contradiction to the theory of relativity, because wherever the n is less than 1, the velocity one needs to consider in this context is not the phase velocity, but the group velocity. And of course, in still certain other cases where group velocity even cannot resolve the case, you actually consider something known as a signal velocity. And whatever, if you either consider the group velocity or the signal velocity, you will notice that the signal itself is not propagating faster than the speed of light. In other words, causality is not being violated, which implies that the Einstein's postulate is correct, that c is the fundamental constant of nature, beyond which or equal to which we cannot send any signal. So, even though we may have a refractive index less than 1, which implies a velocity of speed greater than or the speed of electromagnetic wave in a medium greater than that of speed of light, this does not violate in any sense the principle of causality, which implies that the signal or the information cannot be transmitted faster than the speed of light. So, this is important to keep in mind, but we will briefly consider in these set of lectures not n is less than 1 materials, but materials wherein, and n is less than 1 materials have been found, for instance, in Bose-Einstein condensates, wherein light can I mean there are special materials which have been created where light has been slowed down or light has been speeded up, but we will not talk about those materials, but we will briefly take up what is known as negative refractive index materials. In reality, these are not really materials, and you should note that they are actually typically structures. Of course, we know the difference between materials and structures. When we refer to the word material, we imply that there is no geometry, there is no other parameter, it is kind of an infinitum, and no point in the material is different from any other point in the material. Of course, the properties may be direction dependent, but the points in the material themselves are all identical. In a structure, there is some geometry. Suppose I talk of material like copper, I assume that it is a big block of copper wherein 2 points are identical. But suppose I am talking about a copper plate, then there is a geometry involved in it, because there is a length, there is a breadth, there is a thickness to this plate, and therefore, such a thing would also have a characteristic of a structure. Now, in these negative refractive index materials, the refracted beam will be on the other side of the normal. So, this is a very strange kind of a phenomena, wherein and these kind of materials sometimes are called metamaterials, in which the incident ray comes normally like this, and the normal refracted beam is like this. And if if you are talking about an optically denser medium, this blue material, then you would notice that if this is the theta incident and this is my theta refracted, then theta refracted would be less than theta incident, we know this. But in the case of negative refraction, actually the refracted beam lies on the other side of the normal. So, this is a very special kind of refraction which is known as negative refraction. This was theoretically postulated quite some time back, but then it is physically realized, especially for radio waves and other kind of electromagnetic radiation in quite recent times, the last couple of decades, and it is actually a region area of very active interest, because people are talking about making cloaking devices based on negative refractive index materials. Now, we talk about a few more other aspects, wherein we are talking about interaction of electromagnetic waves with what you might call matter, and for now we will restrict ourselves to what you might call crystalline form of matter. In other words, there is a periodic array of atoms in the material, and of course, I have just shown one row of atoms, and this could be actually a series of rows like in a 3-dimensional crystal, and I assume now for this spacing between the atoms is A, which is now the interatomic spacing or the lattice parameter. And I have 3 positions, 3 situations shown here. Case 1, that the wavelength of the radiation lambda is much larger than the interatomic spacing. The second position is that the wavelength of the incoming radiation is of the order of the interatomic spacing, and the third case is when the wavelength is much smaller than the interatomic spacing. The easiest of these 3 to visualize is the fact that when wavelength is very small, then essentially transmission dominates, which is very easy to see, like it is the case like we drew here, that when you have these point scatterers very far apart, then the radiation essentially can go unimpeded through space. But the remaining 2 are the more interesting cases. Well, one example light to site of transmission, for instance, suppose I am sending light through a material, then the wavelength is for instance, I take copper and send light, then you would think that the wavelength of light is much larger than the interatomic spacing. But suppose I send what you might call an electron beam, which is what you do in a transmission electron microscope, then the wavelength of that electromagnetic what you may call the electrons, which is basically because of the de Broglie relationship, we have a wave particle duality, and this implies that the wavelength of that electron beam is actually much smaller, it is of the order of picometers, and this depends on, of course, on the voltage of the accelerating voltage, but this picometer sized or the wavelength radiation can actually pass through matter as if there existed none. So, this could be a situation very close to transmission when the lattice parameter, say, of copper is of the order of few angstroms. Now, the other 2 situations, the case of the scatterer spacing being of the order of the wavelength here or much smaller than the wavelength, are of interest to us. In other words, the wavelength is much larger than the scattering spacing, are of interest to us, because the first case leads to essentially what you might call reflection. So, most of the wave, when the lambda is much larger than A, is actually reflected, and of course, a little bit of the radiation will still leak through, and this will be a small amount, and this amount which leaks through is frequency dependent obviously, or the wavelength dependent, and it is given by the Bethes relationship. Now, a nice example of this would be, again we go back to our microwave oven. When you look at the microwave oven, you would notice that in front of the microwave oven actually you have a mesh, a wire mesh. So, it is typically a small, there are a lot of small holes in the mesh. In other words, I schematically draw this wire mesh as a mesh like this. So, this is my front window, I will just assume it schematically to be my front window, and there are these small holes in the front window. So, you might assume that the electromagnetic radiation, in the case microwaves, and these microwaves have a wavelength of the order of about lambda of the order of about 3 centimeters, would actually come through these holes, come out through these holes, and actually can affect you, in other words, can heat you up or can cause damage to your tissue. But this does not happen, because this is the case we are now considering, in which case the wavelength is much smaller than this whole dimensions, or in other words the scattering spacing. So, because the wavelength is much larger, most of the electromagnetic waves is actually going to be reflected. In other words, the microwave is not much of the microwave is going to be reflected from those meshes, and nothing is actually going to be, or very little is going to be actually transmitted through that kind of a whole kind of a structure in a microwave oven. Another example could be, for instance, when you are using radio waves to collect, you typically have a radio wave antenna like this, and you might have noticed that many of these radio wave antennas actually have a parabolic or a kind of a shape, and they have these what you may call rod like structures, or they may even have a mesh like structure. And if you look from the side, you will notice that this dish has a collector here. In other words, electromagnetic waves are reflected, and there is a detector here, a transponder or transducer, which converts this energy into electrical signal. Now, the question which may be asked is that, again, if this is such a holy structure, most of it is actually rods or wires here, then won't the electromagnetic waves go through it, and not very little will be reflected. Here again the answer lies, because this scattering spacing or the holes are actually much smaller than the wavelength of the radio waves, which implies that you are actually, even though it looks like a structure which has practically holes in it, you would actually see that most of it is reflection dominant. In other words, this can now act like almost like a mirror we use in a normal telescope. A mirror reflecting telescope has these kind of large mirrors, and these large mirrors actually reflect. So, for what is for light, those mirrors is for radio waves, these kind of dish antennas. Now, equally interesting to this case is the case where in the wavelength of the lambda is of the same order of the interatomic spacing, and now we said we are going to consider actually point scatterers. We will have to for now assume this is slightly different from these cases, because here we have finite thickness scatterers, but for now for simplicity we will assume that these are point scatterers. So, when the lambda is much of the order of A, then we note that actually that you have a phenomenon of diffraction. In diffraction, what happens is that not only you have a transmitted beam, but the energy is redistributed in between a transmitted beam and many of the diffracted beams, and of course, the distribution is not equal. Most of the energy goes into the transmitted beam, very little of it can be found actually in the diffracted beams. But if it is a crystalline material, then the diffracted beams given by Bragg's equation would occur at very specific angles. And of course, we can conduct a diffraction experiment using light in photonic crystals. We can conduct, in other words, we will have to use laser on photonic crystals to get a diffraction, or a optical grating as you call it. You can use an optical grating and laser to get a diffraction pattern. You can use X-rays, and you can use a crystal like copper to get diffraction patterns. You can use microwaves, and you can use a crystal made up of ball bearing balls. In other words, I can take large macroscopic crystals in which there are ball bearing balls, and I use microwaves like we just now pointed out, like in a microwave oven, and I can do a diffraction experiment. So, these three possible outcomes have to be kept in our mind, and for now we have been talking about electromagnetic waves, but we have to remember diffraction and transmission are more common or more universal than just for electromagnetic waves. And we know that, for instance, an Young's double slit experiment can be performed in a ripple tank. In other words, you can use water waves, and you can use what you may call wooden blocks as scatterers to actually get scattering and interference in a water tank. That means, we are using mechanical waves, transverse waves on the surface of water, and those will show the phenomena like diffraction, interference, etc. So, these are universal phenomena, and we have three regimes in which we can talk about. Before we go to the origin of color, let us briefly summarize what we have been talking about so far. In optical properties, we noted that there are three phenomena which can take place. One is refraction, another is reflection, and then third is absorption. And we said that this is basically occurring when you have electromagnetic radiation falling on a medium, which we assume to be denser than the outer medium in which it is immersed. But we said from a fundamental perspective, there are only two kinds of phenomena. One is known as scattering, and the other is absorption. And we also said that if the absorption is possible, if this external electromagnetic wave sets up some kind of an electronic, vibrational or rotational resonance within the material. And of course, once the material has been excited using this kind of an external electromagnetic radiation, the material may relax back, and in the process actually re-emit electromagnetic radiation. This re-emission, of course, we noted can take place immediately, which is why when it is called scattering basically. In other words, the material behaves like the atoms in the material act like dipole oscillators, and it is nearly, of course, with a small time lag re-scattered back, in which case you call it an oscillator, and this is not called an excitation. And we also said that the velocity of light in a optically denser medium is smaller than the velocity of light in a rarer medium like air or vacuum, and which implies that there is a quantity called as refractive index, which is the ratio of the velocities. We also pointed out that this refractive index actually has a frequency dependence, which gives rise to the familiar phenomena known as dispersion, which means that white light is actually spread by a prism into its component colors, which is known as the Vibgyor colors. And we said that there are mechanisms like orientation, electronic, ionic and space charge polarization, which lies at the heart of this kind of a frequency dependence of n or the refractive index. And we also said when it talks about refraction, there are interesting materials known as negative refractive index materials, wherein the refracted beam actually lies on the same side of the normal as the incoming beam or the incident ray. And we also said that this, when you have an electromagnetic wave interacting with a crystal, which is a periodic array of point scatterers, then there are three phenomena possible. One is reflection, other is the interesting case of diffraction, and finally transmission is also possible. And of course, depending on various other parameters, all these three might be simultaneously happening. It is not that we are talking about dominant regimes, but does not mean preclude that only one will happen. Even in case where reflection is taking place, there some amount of matter is actually transmitted, and this has some kind of a lambda power 4 dependence. So, the next topic we take up is the origin of color. Color can arise from various mechanisms as outlined below. The most common what we are accustomed to is the absorption or emission colors. That means that some part of the electromagnetic spectrum is absorbed, the remaining is transmitted, and therefore, you see a certain color, or some part of the electromagnetic spectrum is actually absorbed and the remaining is reflected, and so you see what is called reflection colors. Of course, this absorption may be followed by emission, and this emission can give rise to colors as well, and we will take up especially this topic of absorption and emission colors in nanoparticles. Color again, if whatever is not absorbed or reflected is transmitted, and if some part of the electromagnetic spectrum is actually absorbed, some other part is reflected, but then if you are looking at a transparent material, if you are standing on the back side of the transparent material, then what you see is a transmitted color, which is a complementary in some sense if you are talking about a material which only reflects and absorbs. So, if you are one side of the partially absorbing, partially transmitting system, you will observe one color, but the complementary color would be observed on the other side which is transmitted. Now, you could also have scattering colors, as we pointed out, like in this case of the blue sky or the red sky in the evening, which is basically coming from the scattering phenomena, and we will take up one such example of colloidal gold, wherein you see colors because of scattering. We also know that dispersion itself, like the case of the prism, can give rise to colors, in which case a white light which is being split, and therefore, you have colors. Also interesting are the cases of interference colors, like we know the case of oil films on water, they have a certain color, and this color changes when your viewing angle is changed. You have colors on a CD, a compact disc, you see that on the back side of a compact disc, typically you see some kind of iridescent colors, which is coming from again from interference. The colors of a butterfly wing, for instance, many of these monarch butterflies etc., have a beautiful iridescent color, which is coming from interference, and typically many of the blues in nature are actually interference colors. Many of the birds which also have blue color comes from these interference colors. And we have already noted that if these colors could come from atomic electronic transitions, like for instance, if you look at the yellow color of sodium in a flame test, we have for instance the 3s state and two closely spaced 3p states, and when relaxation takes place from these excited states, we have the two famous sodium vapor lines which are in the yellow region, and therefore, this is coming from emission. So, this is a nice example of an emission color. So, this can be the, for instance, the sodium color, sodium in a flame test or a sodium vapor lamp. Now, in other words, there can be multiple origins of color. It can come from absorption or emission, reflection or transmission, or a combination of all these factors, like absorption, so part of the spectrum is absorbed, part of it is reflected, part of it is transmitted, and therefore, you may have depending on which side of the medium you are, you may observe different kind of colors. Therefore, and there could also be scattering colors, as we just noted the case of the blue sky or the red sky in the evening. There could be colors because of dispersion, and more interestingly, there could be iridescent colors becoming because of the phenomena of interference. In other words, white light falls on a, for instance, a film of oil on top of water. For instance, you have an oil and a water. So, this is my oil on water. Then typically what happens is that some part of the electromagnetic spectrum, this thickness is destructively interfering, and some part of the electromagnetic spectrum, this delta happens to be integral multiples of lambda. That means that it is going to be constructive interference, and therefore, you will see some colors being removed from the electromagnetic spectrum, while others are enhanced, and therefore, you have colors in this coming rise purely from interference. So, we will have a little more to talk about this origin of color in nanomaterials in some of the coming slides. What happens when an electromagnetic radiation falls on a metal? Now, this picture we are taking up because we said that when you have a series of scatterers and you have an electromagnetic radiation falling on it, there are 3 possible scenarios, but this is assuming that these point scatterers are virtually inert point scatterers, but then we know that we could actually be talking about these point scatterers like ion cores in a metal residing in an electron gas. That means, we are talking about metallic bonding where there are free electrons available in the material. In such a material, obviously, the behavior is more complicated, and what really does this electromagnetic wave do to this material is that it actually excites what are known as plasmons. Like you have phonons for lattice vibration, plasmons are collective oscillations of free electrons. So, when you have an electromagnetic radiation impinging on a metallic surface, it excites plasmon waves or oscillations inside the material. Typically, what we call bulk plasmons or longitudinal oscillations of electrons with respect to the ion cores. So, the plasmons which is excited in the bulk of the material is has a longitudinal character, like we have sound waves traveling through a medium like air in this room, which are longitudinal oscillations. On the other hand, suppose I pluck a guitar string, we know that is a transverse oscillation. Now, because the incoming electromagnetic wave sets up plasmon oscillations, this implies that this material there is an resonance happening. That means, an external electromagnetic field wave is going to be absorbed by the medium, because now it is going to set up these electromagnetic or oscillations of the free electrons, which we call plasmons. Therefore, because of this plasmon resonance, what is happening is that you typically find metals are opaque, metals do not transmit light. We will see that this is true for the visible radiation. We will have take a more detailed picture that what kind of a wavelength, how it interacts with the metal in the coming slides, but this is true for visible radiation. Typically, we find that metals are opaque to the visible radiation. Again, we will take up one more interesting case later on, wherein you make thin films of a metallic material like gold. So, thin films of metallic material can actually become transparent, and this when we pointed out about how the properties of nanomaterials come about, in those lectures we talked about a phenomena that when there is insufficient material, then you would have certain effects coming, like for instance transmission through gold, and this is not really a nano phenomena, this is not something new physics coming in, just there is insufficient material. Suppose I did a Bragg's equation on a material on a point scatterers like this. If I had an infinite array, a 3-dimensional crystal, and I throw electromagnetic radiation, then I would obtain sharp delta peaks in reciprocal space. But suppose now I had a finite crystal, there will be a peak broadening, and this peak broadening is essentially coming from insufficient number of atomic planes, and this is no new physics out there. Similarly, you will notice that when you make thin gold foils, they actually can become transparent to some parts of the electromagnetic spectrum, but we will take up these cases in detail very soon. So, we are seeing that when you have an incoming electromagnetic radiation, we have to worry about something more than just the presence of the ion cores or scatterers. We have to worry about the free electron cloud surrounding these ion cores. These free electron clouds are set into collective oscillations, and these collective quantized oscillations are called plasmons, and these plasmon oscillations or resonance can actually give rise to absorption in a metal. In other words, metals are not transparent as we know. Now, what is the regime of transparency and opaquency of a metal? So, when we talk about visible radiation, we have already pointed out what really happens, and that is of course for a typical metal like silver, for instance. But what is the scenario when you have, for instance, the entire electromagnetic radiation starting from gamma rays with very high frequency, about 10 power 23 in the circular frequency, or about 10 power 22, 3 into 10 power 22 in the linear frequency. Then, and on the other hand of the frequency regime, you have the radio waves, which have very long wavelengths of the order of about 10 power 4 meters. That means, you have wavelengths of the order of kilometers. You have these extremely short wavelength 10 power minus 14 meter gamma rays on one end of the spectrum, and you have wavelengths of the order of kilometers. Obviously, all these different regions of the electromagnetic spectrum are not going to interact identically with a given metal. So, what are the factors which come into play? So, we can actually divide the electromagnetic spectrum into 3 frequency regimes, and these 3 frequency regimes, 2 of them come in the range of the high frequency regime, and one of them is the low frequency regime. How do I determine my high or low frequency regime? I multiply my frequency, or of course, omega being the circular frequency, with the mean free collision time which we had encountered before, and typically we had noted that the mean free collision time is a collision time between of electrons between, in other words, it accelerates or maintains increases velocity between two collisions, but then it may then interact with a phonon or an impurity and get scattered, and the time between the two is called the mean free time more casually, or the average collision time, which happens to be of the order of about 10 power minus 14 seconds for most metals. So, I multiply my circular frequency with my mean free time and note if it is less than 1 or it is much greater than 1. So, let us take an example, for instance, of the case of copper, and when you are talking about a frequency like 10 power 7 hertz, and we see that this electromagnetic radiation is actually absorbed, and of course, some of it will be reflected. Now, in making these discussions, as I pointed out, we have to invoke the concept of plasmons, right, and plasmons have a certain characteristic frequency depending on the material, and this plasmon frequency typically lies in the range of about 10 power 15 hertz. So, suppose I am talking about the plasmon frequency, which is given which is a function of the what you might call the electron density, and of course, also depends on the free electron mass and the permittivity of the medium. This plasmon frequency lies in the range of about 10 power 15 hertz. For gold, for instance, is 2.18 into 10 power 15 hertz. So, what is happening now is that in the low frequency regime, the beam penetrates the metal for a short distance, which is called the skin depth, and then it is absorbed and some of it is reflected. And when I am talking about the low frequency regime, which is a reflecting and absorbing regime, I am talking about the regime on the right hand side. So, this is my low frequency regime. So, herein reflection and absorption is being dominated, and what is my switchover dominant or the switchover kind of frequency which I have to monitor? This is the plasmon frequency, and I noted that this plasmon frequency is of the order of 10 power 15 hertz. In other words, in the omega scale, this is my 10 power 15 here. So, my plasmon frequencies are approximately in this regime, and my visible lies to the right of the plasmon frequencies. That means that in the visible region, metals are reflecting and absorbing, they do not transmit any of the radiation. So, bulk metals typically we know that, we already have this experience that they do not transmit any of the radiation. In the high frequency regime, wherein the omega tau is greater than 1, and we see that this is of course coming in the visible and the ultraviolet region. There are two possibilities. When omega is less than omega p, that means this region where the omega is actually less than omega p, this region to the right of it, the visible and the infrared regime. So, you have the to the right of the plasmon frequency, you have the visible and the infrared, which is actually the low frequency regime, given in the of course, the high frequency regime wherein omega tau is much greater than 1. In other words, I have the low frequency regime where I know that metals are not going to transmit, then I take up the high frequency regime, but then subdivide into two parts, that part where the omega is less than omega plasmon and the case where omega is greater than omega plasmon, noting that the omega plasmon is of the order of 10 power 15 hertz, which lies somewhere in the frequency spectrum somewhere here. So, the visible and infrared are actually larger frequencies compared to the what you might call the omega plasmon. So, in this high frequency regime, you see that visible and ultraviolet radiation is actually reflected, because this regime lies because the plasmon frequency is less than the or greater than the omega of the radiation. But suppose you go to a regime where omega is much greater than p, then the metal becomes a non-absorbing transparent dielectric. So, if you are in this regime wherein the omega is much larger than omega p, so you are somewhere here, then you would notice that for radiations like gamma rays and X rays, a metal can actually become transparent. So, you have three kind of interactions possible of radiation with a metal. One regime in which is absorbed and reflected essentially, other regime wherein the visible and ultraviolet regime where there is reflection, and there is another regime wherein you can actually see that the metal actually becomes some kind of a transparent dielectric, which happens only in very high frequency regimes. Now, having this broad picture, that means metals have to be treated slightly separately from semiconductors and other dielectrics. So, we see when we talk about a dielectric like glass, we know, or as a SiO2 crystal, we know that I do not have to worry about plasmons at all. That means, I can talk about purely in terms of the normal language of a transparent dielectric, except close to those resonances wherein the dielectric starts to absorb, and we already noted the mechanisms of those resonances. But when you are talking about a metal, the predominant behavior of metal to electromagnetic radiation is coming from these free electrons and of course, when these free electrons stop to respond in the case when the omega is much greater than omega p, then you note that actually the metal can also become transmitting to an electromagnetic radiation, as it may happen to high gamma rays, etc. The optical properties of a semiconductor, as you would expect, is going to be very different from that of a metal, and this is going to be obviously dominated by the phenomena of the band gap. So, we will take up briefly here what are the issues of the band gap, how is it going to affect my absorption and emission from a semiconductor, and we are talking about absorption and emission of electromagnetic waves. Now, and we will take up in somewhat detail the fact that what happens when I make a semiconductor particle like CDAC or gallium arsenide in a very nano form. That means, I have a particle size of the order of 10 or 20 or 5 nanometers. Ionic crystals show strong absorption and reflection in the infrared region due to interaction of light with the optical phonons, because now the absorption is not because of plasmons, because there are no free electrons in this system. This is a semiconductor, and this ionic material, which is a dielectric, tends to absorb in the infrared region, because now you are setting up resonances in the optical phonon spectrum. Compound semiconductors have a partial ionic character and also exhibit absorption and reflection in the infrared. Like when we are talking about compound semiconductor, it can be the direct band gaps gallium arsenide or gallium phosphide, and these have a certain partial ionic character, which implies that they also have a partial behavior which is similar to ionic crystals. Now, if the energy of the incoming photon is greater than the band gap, then the photon is absorbed. So, you have the valence band in a semiconductor, which is schematically shown here. You have the conduction band, and you know in a semiconductor at 0 Kelvin the valence band is full and the conduction band is empty. And if you are at a finite Kelvin temperature, you know that thermal excitation of electrons will put some electrons into the conduction band, and we know that this fraction is given by the Fermi-Dirac statistics. Now, what is happening is that if I am sending electromagnetic radiation, and the measure of the energy of the electromagnetic radiation is its frequency, and if the frequency is much smaller than the critical frequency given by Eg by h, then there is no absorption, unlike that of a metal, because there are always free electrons which can be oscillated. But now, if you keep on increasing the frequency, then the energy in the incoming photon can exceed that of Eg. In other words, an electron can be excited from the valence band into the conduction band, and you leave a hole in the valence band. A hole is nothing but the fact that there are actually now n minus 1 electrons in the valence band. I can either deal with the motion of these n minus 1 electrons in opposition to the electric field, in a direction opposite the electric field, or I can talk about the motion of one hole in the direction of the electric field. So, this is the convenience I use. The language of hole is for convenience. So, I do not have to deal with n minus 1 electron, but I can just talk about one hole moving in the valence band. Therefore, I would have a strong absorption when my frequency exceeds this critical frequency of the absorption edge, and we will therefore absorb the semiconductor will absorb the electromagnetic radiation. Now, as the wave vector of a photon in the optical region is very small, and only constant momentum transfers are allowed across the band gap, vertical transition and K space are allowed. That means that if I have a direct band gap semiconductor, I can ignore the wave vector of the photon, incoming photon, because it is very small, and I can only talk about the energy transition. So, that I need to not have to worry about the what you call the momentum of the photon. But on the other hand, suppose I am talking about an indirect band gap semiconductor, in which case the conduction band is actually shifted in K space. That means, the conduction band minima lies at a certain fixed value of K here compared to the maxima in the valence band in energy. This implies that when I want to excite an electron to from the valence band to the conduction band, then not only have I to supply the energy Eg, but additionally I will have to supply, if I will just to add and subscript, call a kg kind of a momentum. Now, as I pointed out, the photon itself does not have this momentum. So, this would imply that purely by a photonic excitation, I cannot excite an electron from the valence band to the conduction band, but luckily a phonon comes to our aid here. That implies that in indirect band gap semiconductors like germanium, both a photon and phonon together give rise to the excitation, and in this case of the phonon I ignore its energy, like for the photon I ignored its momentum because it was small, for the phonon I can effectively ignore its energy because its energy is small, and I can think of the phonon only contributing only the momentum to the electron. So, I have now two aspects coming in when I am trying to excite an electron in the indirect band gap semiconductor. One is the energy coming from the photon, the other is momentum coming from the phonon, and put together they supply the required momentum and the energy to excite a electron from the valence band to the conduction band. Typically, the band gap of semiconductors of the order of about EVs, a few EVs, that implies that the fundamental edge actually is in the infrared, and therefore, semiconductors though cannot be used as lenses in the visible region, because semiconductors are not transparent in the visible region, but you can make infrared, when you make infrared cameras, lenses can be made out of these semiconductors, because below the absorption edge they actually would transmit, and therefore, I can make a lens out of a semiconductor. Now, therefore, to summarize the optical properties of semiconductor, the optical properties of semiconductor are dominated by two factors, one of which is given in this slide, the other one we will take up in the next slide, is the fact of the band gap. That means, any energy or frequency which is lower than the critical energy or the critical frequency is not going to be absorbed. On the other hand, any other higher energy than the band gap is going to be absorbed by the semiconductor, and later on we will have a lot to say about how this band gap actually changes with confinement. How do you make it when you make the material smaller, how the band gap changes. And we said that in the context of absorption in semiconductors, not only have I to worry about this band gap energy Eg, I also have to worry about the relative position of the conduction band minima vis-a-vis with respect to the valence band maxima. So, this could be a direct band gap semiconductor in which the minima lies right above the maxima, or it could be indirect band gap semiconductor, in which case there is a shift of the minima with respect to the maximum of the valence band in the K space, in the momentum space, which implies that I have to supply the energy coming from a photon ignoring its momentum, and the momentum coming from a phonon ignoring its energy, and put together the phonon and photon actually give rise to an excitation of an electron from the valence band to a conduction band. When I said that two factors come into play when I am talking about absorption in semiconductors, the second factor is what is called the exciton. Now, having excited an hole, I mean excited electron to the conduction band, you are left with an electron in the conduction band and a hole in the valence band. So, you have these two factors, you have a hole in the valence band and you have an electron in the conduction band. But in principle, of course, you might assume that these hole would move in its valence band independently in response to an electric field, of course, dictated by its mobility in the valence band, which would be different from the mobility of an electron in the conduction band, and you would assume that this electron would move freely in the conduction band. This situation may or may not be so. In fact, there would be an Coulombic attraction between the electron and a hole, and you may form what is called a bound state between the electron and the hole, which is called an exciton. So, an exciton is a bound state of an electron and a hole. This binding is due to electrostatic or Coulombic attraction, and the exciton has a lower energy than the unbound electron plus and hole. So, obviously, because there is a lowering of energy, that this binding is taking place, and this implies a very important thing, that brings the energy levels closer to the conduction band. So, what is exactly happening is that, so you have the conduction band edge and you have a certain Eg. That means, if I do not supply my Eg, then I cannot excite an electron from the valence band to the conduction band. But because of the Coulombic attraction between the hole and the electron, you can have a bound system, and this bound system has an lowering of energy with respect to the conduction band, and this is now my exciton binding energy. So, this small number here, and this exciton binding energy is typically very small, it is of the order of 0.01 eV or about 10 milli electron volts. This is a small binding energy. Nevertheless, this energy is lower than the conduction band edge energy. This has important consequences to the absorption of a semiconductor, as we shall see now. But so, this exciton forms, and what is this exciton? This is a bound state, and typically we will see that this exciton can be thought of as an electron and a hole moving around. That means, they are spatially confined and they are moving around each other's center of mass, and this it can be calculated, this radius around which they move around can be called as the Bohr exciton radius, which is given by some of the fundamental constants of an electron, and this Bohr exciton radius is of the order of about 11.8 nanometers. So, it is in the nanoscale, it is not like the normal Bohr radius of an hydrogen atom, which is much smaller, as you know. Therefore, you can have an electron and hole in a bound state, and therefore, they are spatially localized. A few more factors we will see how when this localization can break down, but we have introduced a new concept called the concept of an exciton, which is now spatially bound, and spatially bound means that it is spatially bound to a radius of the Bohr radius we just now pointed out. They move around the center, you can think of them as moving around a common center of mass, and this give rise to an energy level, the bound level of an exciton in the band gap. So, this is very important, and this exciton is an electrically neutral quasi particle, because now there is a hole and electron together, they form a neutral quasi particle that can exist in insulators and semiconductors, and we will talk about the relevance of excitons only in semiconductors here. The exciton can be thought of as an elementary excitation in materials, which can transport energy without transporting electric charge, because this sum total of the electron and hole is a neutral particle. This is when it moves through the crystal as in the bound form, this can be thought of as transporting energy without transporting electric charge. This excited state can travel through a lattice without transfer of charge. So, this is very important, and for now we will restrict ourselves to what is known as a free exciton, or otherwise given the name as a Mott-Wiener exciton, which can move through the crystal. There can be other forms of excitons which are known as bound excitons, which we will not talk about here. The exciton can itself be thought to have as an effective mass, an effective reduced mass, which depends on the effective masses of the electrons and holes as given in this formula. And if you look at the effective mass of an exciton, you can see that, and for example, I am taking gallium arsenide here, it has got a mass of about 0.059 MeV. In other words, it is much smaller than the mass of an electron. So, exciton can be ascribed an exciton Bohr radius, similar to the concept of an Bohr radius in a hydrogen atom. An exciton can be given a mass, which is the effective mass or mu star of an exciton, which is, of course, as we just now saw, it has a much smaller value than the electron mass. That means, a much lighter particle, quasi particle, as you should be more careful with this terminology, because it is a quasi particle as compared to an electron. Now, we have seen that the photon absorption by semiconductor can lead to the formation of an exciton. The exciton binding energy for most semiconductors is of the order of few to few tens of milli electron volts. So, this energy we already seen that it is much smaller, the exciton binding energy is much smaller than the typical band gap energy of semiconductors. This is very important note. For instance, the exciton energy in gallium arsenide is 4.6 milli electron volts. For cadmium sulfide, it is of the order of about 28 milli electron volts. So, this is the range of these binding energies of this exciton. And if you want for a comparison, Kt at room temperature is about 40 milli electron volts. This tells you directly that since Kt at room temperature, I am now talking Kt at room temperature, and Kb is the Boltzmann constant, is greater than the exciton binding energy. This implies that at room temperature in bulk semiconductors, the exciton will be unbound. The thermal energy will overcome the binding energy of the exciton, and implies that the exciton actually will be dissociated at room temperature. So, that we implies if you take a room temperature and do the electromagnetic radiation absorption experiment, then you would note that there will be no peak corresponding to the exciton. Okay. And if you want to take a even higher energy scale, you will note that the binding energy of an hydrogen atom is about 13.6 electron volts, much larger than the exciton binding energy. So, we note that we have an important concept like exciton, but it becomes important only at low temperatures and absorption of semiconductors. One of the reasons we are taking up this discussion of excitons in details is that often when we read literature regarding nanoparticles, semiconductor nanoparticles and their absorption, the word excitonic absorption is used. And this sometimes can be misleading, because the actual effect is coming from confinement effect and not from excitonic absorption, because, and therefore, we have to be a little careful with the terminology and the physics behind it. And if you look at a semiconductor low temperature, then the excitonic absorption spectrum is a sharp line just below the fundamental edge of the semiconductor, and this is observed at low temperature where thermal energy is lower than the binding energy. So, if you go to low temperature, the KTB contribution goes down, the exciton binding energy is larger than KTB, which implies that I would observe an excitonic absorption. And for now I am just showing one excitonic level, a simplified diagram, wherein I would have an absorption corresponding to the exciton just below the fundamental edge of the. So, I am plotting h nu minus E g in electron volts as a function of the absorption coefficient, and for a normal semiconductor without the exciton, you would note that the absorption coefficient would go increase like this. This is a theoretical plot, but in the presence of the exciton you will observe a strong peak here, which is now my excitonic peak, which can be observed only at low temperatures. So, because now even though the energy level is only slightly below the conduction band edge, but statistically this implies that many more electrons are going to be excited to the exciton level, and which gives you a strong absorption, excitonic absorption. Now, an important point we already saw, the case of the exciton radius is the fact that the exciton radius itself is a nanoscale subentity within the semiconductor. So, it is a critical number within the material, which is the exciton binding radius, which is of the order of nanometers. For instance, for gallium arsenide, with an exciton energy of about 4.6 MeV, sorry, milli electron volts, the exciton radius is of the order of 11.8 nanometers. The bulk band gap is of the order of 1.43 eV, which is much larger than the MeV quantities. For CDSC, the exciton radius is about 5 nanometers. For CDS, it is about the order of about 3 or 4 nanometers. And if you look at a slightly more detailed picture of the exciton, you can actually see that you can ascribe quantum numbers to the excitons. In other words, the lowest, and this is of course an exaggerated picture, because we know the exciton energy is very small, and you have the compared to the band gap energy, this is out of scale diagram. So, we should note that this is like the previous diagram I showed you, and you can see that in this you can have multiple quantum numbers. So, this could be the n equal to 1 state, and n equal to infinity state is nothing but the conduction band gap edge. The conduction edge itself becomes the infinity state. So, therefore, you can have multiple levels, excitonic levels, and therefore, you can have multiple excitonic absorptions, and they will, suppose you look at a spectrum like this, the other excitonic absorptions would also show up in such a spectrum, and you have to go to low temperatures for this. But then these excitonic levels can also be thought of as quantized levels having quantum numbers of its own. And we can note that if the crystal becomes very small, of the order of the excitonic radius, then there are important things which we need to consider.